Today on Flipping Science, I'm going to be looking at changes in equilibrium and how to interpret these from graphs. So here's an example. We have a system at equilibrium. We've got N2O4 and NO2 again. If we look at what's happening at this change here, what's happened? What have we done to this system that was at equilibrium over here, but now the position of equilibrium has shifted and we've moved over here? If we look at what's happened, our NO2 concentration here has sharply increased. So what's happened is the system was at equilibrium over here, someone's added some NO2, and now the system is responding. So if we increase our amount of NO2, the position of equilibrium is going to shift over to the left to reduce the concentration of NO2, but increase the concentration of N2O4, and that's what we see in this graph. So we talked about concentration, what happens last time, and this is what happens on the graph, what you would see on a graph. So you'd see a sharp increase or decrease of one of the reactants or products. So that's what happens with concentration. With pressure, we're talking about gaseous systems. You get, at a certain temperature, you get a certain number of molecules in the gas phase. This is the ideal gas law. Worry about that in uni. If you reduce the number of particles in total, that means you lower the internal pressure. If you increase the number of particles in total, that means you increase the pressure. So the system will shift to reduce the stress by looking at the total number of particles that are being produced. So if you increase the pressure by reducing the volume, the position of equilibrium shifts to reduce the total number of molecules that are in your mixture. And if you reduce the pressure by increasing the volume, then the position of equilibrium shifts to increase the number of molecules in the container. So it stays about the same. So let's have a look at what happens when we mess around with the pressure of a system at equilibrium. So here's our equilibrium here, so N2O4 and NO2. If I look at this, I've got one molecule of NO2O4 on this side and two molecules of NO2 on this side, and this is going to be important. So what happens when I increase the pressure on this side over here? So I'm going to use my plunger and my beaker, I'm going to squish it down. That means now I've got the same number of molecules, but they're in a smaller space. So essentially I've increased the concentration. So if I increase the concentration of the gas molecules, I want to change the position of equilibrium to reduce the total number of gas molecules. So on this side I've got two, on this side I've got one, so the position of equilibrium is going to shift to the left. So it's going to reduce the concentration of NO2 and increase the concentration of N2O4. That means I'm going to have more of this and less of this. That reduces the pressure internally because now I have less molecules. I've gone from 2 on this side to 1 on this side. So over this side I'm going to reduce the pressure. So I'm going to raise my plunger up. That means I've got more space for the same number of molecules. That means the pressure is going to reduce. So what I want to do now is I want to make more molecules so that I get back to equilibrium. So the position of equilibrium is going to shift to the right over here. We've got two molecules on this side, one molecule on this side. So we're going to make more NO2, and that will lead to reaching back to equilibrium. So here's a graph showing that. So on this side over here, we look at what's happened. So we've got a sharp increase in concentration of both of the gaseous species. So if I increase the concentration of both, what that means is that the volume has decreased, so the pressure has increased. So we've increased the pressure, so to reduce the pressure we're going to produce more N2O4 and reduce our concentration of NO2. So we're going to reduce this and make more of this. So the position of equilibrium shifts to the left, the side with less molecules is going to increase in concentration. So in this case we can see the concentration increase and we can see the concentration of NO2 decreasing. So that's pressure. Now we're going to look at what happens with temperature. Big rule here is if the forward reaction is exothermic, then the back reaction is endothermic, and vice versa. So if we look at our equilibrium again, we can see the forward reaction on this side, our delta H value is positive. That means it's an endothermic reaction. So if the equilibrium goes in this direction, it's endothermic, and if it goes in this direction, it's exothermic. Here on this side here, I'm increasing the temperature of my mix. So which direction does the equilibrium position move? So if I'm heating it up, it's going to favor the endothermic reaction. It's going to favor the absorption of heat energy. So the position of equilibrium is going to move in the endothermic direction, which is over to the right over here. If I cool down the system at equilibrium, so I've got this N2O4 NO2 system, if I cool it down, it's going to favor the exothermic direction. So by cooling it down, it's going to shift position over to the left, which is going to be exothermic. So it's going to produce more heat energy to get back to equilibrium. So here's an example. We've got A2 plus B2 going to AB2, and in this case our delta H value is negative. So the forward reaction is exothermic, the reverse reaction is endothermic. So if we have a look at our graph here, we can see we reach equilibrium and then we get to this point and we have a change. If we look, our concentration of AB2 increases and our concentration of A2 and B2 decreases. So we've had a temperature change on this position on this system at equilibrium, and we need to figure out what the temperature change was. We're reducing the concentration of A2 and B2 and increasing the concentration of AB2. So we're favoring the forward reaction. So in this case, if delta H is negative, that means we need to have cooled down the system. If we cool down the system, it's going to move in the position that produces more heat energy. In this case, it's shifting over to the right, so we're making more AB2. Alright, so let's bring all three of those together by looking at what happens in this situation here. So here's our equation, N2 plus 3H2 goes to 2NH3. We've got our delta H value here and it's negative. So let's have a look at what's happening at each of these positions here when we're changing something. So if we look down here at NH3, we can see that the NH3 concentration is increasing, the H2 is decreasing. We have a sharp increase in the nitrogen concentration. So what that means is they've added nitrogen to the system. That means the amount of nitrogen is going to decrease, the amount of hydrogen is going to decrease, and the amount of ammonia is going to increase because the equilibrium is going to shift to the right. So they've added nitrogen, so extra this, so it's going to shift over this way, so we're going to make more NH3. And that's what we see over here. In this case over here, we see sharp increases in all three concentrations. What that means is, to me, the pressure has increased, so the concentration is increased. So they've increased the pressure. If they increase the pressure, what's going to happen is the shift of equilibrium is going to favor the production of fewer molecules. So in this case, we've got 2 molecules on this side and 4 in total on this side. So 3 from here and 1 from there. So it's going to shift in the position to produce less molecules. So in this case, more NH3. So if we have a look here, so our NH3 concentration increases and our concentration of N2 and H2 is decreasing as well. Look at the last case, we've got an increase in concentration of H2 and N2 and a decrease in concentration of NH3. So we've changed the temperature here, so let's figure out which direction we've done. So the forward reaction here is exothermic. We're favoring the production of the reactants on this side. So if we're favoring the production of reactants on this side, we're shifting the position of equilibrium to the left, which means we're favoring the endothermic process. So if we're favoring the endothermic process, what that means is they've heated up this system. So if you heat up this system, it's not going to favor the forward direction, which is exothermic, it's going to favor the reverse direction, which is endothermic. So there's some examples of some questions that you might get and how to interpret these graphs. That's it for Flippin Science today. See ya.